Dependency inversion. Welcome to this video on the concept of dependency inversion in software development. In today's complex software systems, managing dependencies between different components is crucial for building robust and maintainable applications. Dependency inversion is a design principle that addresses this challenge by promoting loose coupling and modularity in our code base. By adhering to the dependency inversion principle, we can reduce the interdependencies between modules, making our code more flexible, extensible, and testable. It helps us avoid tightly coupling our components, allowing us to easily replace or modify individual parts without affecting the entire system. In this video, we'll explore two approaches to implementing dependency inversion. First, we'll delve into the lower-level approach, which focuses on how classes within our codebase can interact with each other. We'll see how using techniques like dependency injection can break the hard-coded dependencies and enable us to inject dependencies from external sources, increasing the flexibility and testability of our code. Then, we'll shift our attention to the higher-level approach, which involves interactions between services or modules in a larger system. We'll discuss service-oriented architecture and how using interfaces to define service contracts can abstract away specific implementation details and facilitate loose coupling between different parts of our application. Before we dive into the practical implementations of dependency inversion, let's establish a solid understanding of the theory behind it. Dependency inversion is a fundamental principle that stems from the solid principles of object-oriented design. It promotes the decoupling of software components and ensures that high-level modules are not directly dependent on low-level modules. Instead, both depend on abstractions. So what does dependency inversion really mean? At its core, it suggests that modules or classes should depend on abstractions, not on concrete implementations. This inversion of control allows us to achieve loose coupling between components and enables more flexible and maintainable code. By depending on abstractions, we can create contracts or interfaces that define the expected behavior of a dependency. This abstraction shields high-level modules from the specifics of the implementation, allowing them to interact with different implementations without needing to change their own code. This is a powerful concept that enables us to swap out dependencies with ease, facilitating extensibility and enabling us to adapt our software to changing requirements. Dependency inversion also plays a significant role in the testability of our code. By relying on abstractions, we can easily mock or stub dependencies during testing, isolating the behavior of individual components and ensuring that our tests focus on specific units of functionality. This promotes a more robust and effective testing process. Now that we have a solid grasp of the theory, let's explore two practical approaches to implementing dependency inversion. In the context of class-level dependency inversion, we aim to address the issue of tight coupling between classes by injecting dependencies from external sources. This approach is commonly known as dependency injection and is a powerful technique for achieving loose coupling and testability in our code. Let's consider an example scenario where we have a user service class that depends on a user repository class to retrieve user data from a database. Without applying dependency inversion, the user service class would directly create an instance of the user repository class, resulting in a tightly coupled relationship between the two. To apply dependency inversion, we introduce an abstraction in the form of an interface. Let's call it iUserRepository. This interface defines the contract that any concrete implementation of the repository should adhere to. The user service class will now depend on this interface instead of the concrete user repository class. In this example, we can see that the user service class has a constructor that accepts an instance of iUserRepository as a parameter. This is known as constructor injection. By passing the dependency through the constructor, we decouple the user service class from the specific implementation of the repository. Now, when we create an instance of the user service class, we can inject different implementations of the iUserRepository interface based on our needs. This flexibility allows us to easily swap out the repository implementation without modifying the user service class itself. It also enables us to mock or stub the repository during testing, isolating the behavior of the user service class. By applying class-level dependency inversion through techniques like dependency injection, we achieve loose coupling, modular code, and improved testability. This approach is particularly useful in scenarios where we want to manage dependencies between classes effectively. In the context of service-level dependency inversion, we shift our focus to the interactions between services or modules within a larger system. This approach involves abstracting dependencies behind interfaces, promoting loose coupling and flexibility in our software architecture. To illustrate this approach, let's consider a scenario where we have two services: a payment service responsible for processing payments and a notification service responsible for sending notifications to users. Traditionally, these services might directly depend on concrete implementations of each other, resulting in tight coupling and potential difficulties in maintaining or extending the system. To apply service-level dependency inversion, we introduce interfaces that define the contracts or service boundaries. Let's create iPayment service and iNotification service interfaces to represent the respective services. The concrete implementations, such as Payment Service Impl and Notification Service Impl, will implement these interfaces. In this example, the shopping cart class depends on abstractions, iPayment service and iNotification service, instead of concrete implementations. Through constructor injection, we provide instances of the desired implementations, Payment Service Impl and Notification Service Impl, when creating an instance of the shopping cart class. By abstracting the dependencies behind interfaces, we achieve loose coupling between the services. The shopping cart class doesn't need to be aware of the specific implementation details of the payment or notification services. This enables flexibility and extensibility, as we can easily introduce new implementations or modify existing ones without impacting the shopping cart class. Service-level dependency inversion also facilitates modular development and scalability. Each service can be developed and tested independently, as they rely on clearly defined interfaces rather than concrete implementations. This separation of concerns allows for easier maintenance and the ability to swap out services as the system evolves. By adopting service-level dependency inversion, we achieve loose coupling, modular architecture, and improved maintainability in our software systems. This approach is particularly valuable in larger systems where interactions between services are complex. By applying dependency inversion, we achieve several benefits in our software development practices. Loose coupling. Dependency inversion promotes loose coupling between components, reducing the dependencies between modules and making our code more flexible and adaptable. Testability. By depending on abstractions and injecting dependencies, we enhance the testability of our code. We can easily mock or stub dependencies during unit testing, allowing us to isolate the behavior of specific components and write more focused and effective tests. Modularity and scalability. Dependency inversion helps in creating modular code, enabling the development and maintenance of independent modules or services. With dependency inversion, we can easily swap out implementations or introduce new ones by relying on the interfaces or contracts defined for our dependencies, which gives us more flexibility to extend or enhance implementations. In this video, we explored the concept of dependency inversion and its significance in software development. We discussed two practical approaches to implementing dependency inversion: the class-level approach, focusing on dependency injection, and the service-level approach, emphasizing abstraction and loose coupling between services. As you continue your software development journey, remember to consider dependency inversion as a valuable tool in your arsenal. Apply it when designing and implementing your software, whether at the class level, through dependency injection, or at the service level, by abstracting dependencies behind interfaces. Thank you for joining us in this exploration of dependency inversion. Thank you for watching, and I hope to see you in the next video in this series.